For the last 2 years, we have treated large language models like highly advanced search engines. You type a prompt into a chat window, it generates a text response, and the session ends. It is entirely stateless. If you use that text output to build software, you are acting as the manual transmission layer. You copy the generated code, tab over to your IDE, paste it in, run it, find an error, copy the log, and paste it back into the browser. It is a slow loop constrained by human bandwidth. This diagram shows the current architectural leap achieved by models like Claude Opus 4.6 and 4.7. The AI is breaking out of the browser tab and is splitting into specialized interconnected nodes. This turns the LLM from an isolated text generator into an agentic OS, an integrated workspace that retains memory and state. Instead of amnesia between prompts, this system tracks the logic from an initial design mockup, carries those constraints into local code execution, and remembers them all the way through to cloud deployment. We are going to use this architecture to execute a complete software development lifecycle, where a human never writes a single line of syntax. We will map this workflow starting from one text prompt, extract the design logic, pass it to local hardware to scaffold the codebase, and finally automate continuous cloud deployment. By operating the model at the OS level, the machine executes the file transfers, the terminal commands, and the infrastructure setup. The limit on development velocity is no longer human typing speed, but compute. The lifecycle begins here, in Phase 1, prototype to data. Traditionally, building a front-end requires plotting out vectors, shapes, and layouts in standalone design software before any code is written. Claude Design eliminates that intermediate step entirely. You input a single text prompt describing the interface, and the model directly renders a high-fidelity, interactive prototype right in the browser. A picture of a website is useless to a compiler. The visual logic has to be extracted so the machine can read it. We instruct the model to analyze its own rendered prototype and output every design decision into a strict JSON object. This captures the hex codes, the specific typography weights, the grid layouts, and exact padding and margin constraints. That single file is the mandatory bridge. It translates aesthetic choices into a format that a command line interface can parse and apply to a local codebase. By forcing the visual output into structured data, abstract graphic design becomes a deterministic programmatic input ready for an engineering environment. This brings us to Phase 2, OS-level execution, using tools like Claude Code and Cowork. The engine powering this phase is the Model Context Protocol, or MCP. It's an open standard allowing cloud-based AI to securely operate your local hardware. With MCP enabled, the agent gains read and write access, opening your file system and scaffolding the exact folder structures needed for the application. It executes terminal commands to install package managers, initialize frameworks like Astro, and set up Tailwind CSS for styling. The agent then ingests the JSON file we generated in Phase 1, mapping the design constraints to the Tailwind configuration. The resulting code directly implements the prototype's parameters. Modern software does not live in a vacuum. It connects to databases and external tools. This requires managing secure environment variables. The agent uses your local terminal to generate a unique UUID. This serves as a secure API key, acting as the password for the application's external communications. Injecting that key into the environment variables allows the agent to authenticate and sync the application with external systems, pulling in CRM data from Notion or scheduling events via Google Calendar. Granting terminal and API access transforms the LLM into an active developer that executes the build rather than just advising on it. With the local build complete and tested, Phase 3 moves the codebase off your hardware and into remote cloud infrastructure. As mapped here, the agent uses its terminal access to initialize a Git repository, commit the files, and push the entire codebase up to a private GitHub branch. We then connect that repository to a hosting platform like Netlify, establishing a continuous integration and continuous deployment pipeline. Every time the agent pushes an update to the main branch on GitHub, Netlify automatically detects the change and triggers a live build to production. This creates a highly automated system, but it introduces a severe vulnerability. Large language models are inherently stochastic. They predict the next token based on probability, meaning their outputs vary. If you schedule this agent to update your live website while you sleep, a slight variation in its reasoning could break the build. Conversational prompting is entirely inadequate for a headless, unsupervised production environment. To run this reliably, we enter Phase 4, constraining stochasticity using the DBS framework. DBS standardizes AI tasks. The D stands for direction, rigid, step-by-step operational workflows the agent is forbidden to deviate from. The B is for blueprints, providing exact reference examples and specific formatting constraints to limit the available output paths. The S is for solutions, pre-written code scripts for complex actions. All three elements compile into a single skill file, acting as a hard rail that forces chaotic probabilistic behavior into a deterministic outcome. With the skill file locked in, we make the final architectural move. We abandon our local hardware entirely and spin up a remote cloud environment hosted on Anthropic servers. We give this remote environment access to the repository and the DBS skill file. By scheduling a headless task for 6 a.m. daily, the agent can autonomously audit the codebase for necessary patches and push those updates to trigger a Netlify build. If you want an agent to act as a reliable system component, you cannot just give it instructions. Aggressively constraining probability through rigid frameworks is the only way to achieve continuous software automation at scale. We have mapped a unified path. We went from a text prompt generating a visual prototype into a structured JSON file, through local file generation via MCP, pushed to GitHub, and automatically shipped to a live deployed site. The technical breakthrough here lies in system orchestration, prioritizing the management of the pipeline over the mere generation of syntax. We have elevated the LLM to an OS-level actor, capable of coordinating local file systems, cloud databases, and deployment platforms simultaneously. This automated pipeline shifts the daily objective for software engineers. Typing out boilerplate code and manually debugging syntax errors are rapidly depreciating skills. They no longer represent the primary value of an engineering team. The new role of the engineer is architectural. It is about designing rigid constraint frameworks, like DBS, to guide and govern agentic behavior. It requires strictly auditing access protocols, determining exactly which tools the agent can use via MCP, and ensuring data moves securely across the organization's tech stack. Mastering agentic architecture and workflow constraints has become the mandatory baseline for building modern software.